Hi, I decided to jump ahead into chapter 10. Reading through the rest of chapter 9, I thought it was a little too confusing unless you had some basic understanding of network protocols. So decided to uh, again jump ahead to chapter 10. This is one of the core chapters I wanted to cover in this course. Anyway, I felt it's important for um, electrical engineers to have some basic understanding, at least, of how computer networking works. So this actually takes a fairly high-level view at first, and then we'll get in of networks and talks about network models, and then we'll get into a little bit of detail specifically about the network model used by the internet called the TCP/IP model. Next time we'll look at how TCP works over wireless networks, and then we'll also look at the next version of what's called the networking protocol, the IP version 6. Um, so this was one of the first uh, network models that was developed. A network is a network model is considered to consist of different layers. Some of these are hardware, some of them are software. At the very bottom layer in what's called the Open Systems Interconnect model, which is a 7-layer model, is the physical layer, um, uh, that deals with actually the electrical connections. The voltage is actually on the physical connection between two nodes in the network. Above that is the data link layer. Um, there's some error control in this layer, defines how packets are actually formatted on the layer. Again, this deals with connections between two nodes. Above that, we have what's called the network layer. Well, um, I think there's details on subsequent slides, but the network layer basically deals with how packets get beyond the local network, like from wherever you are to across the world. The transport layer deals with different types of services that are provided. We have some transport services that actually provide error correction and flow control, and then others that don't. The session uh, layer deals with has some error control built into it and compression. The presentation layer deals with how data is formatted, and then finally the application is the highest layer, and that's the highest level protocols, and that's how things like mail might work or web services. Um, so again, a little bit more detail. The physical layer is defining the terminations, connections for communication. So the Ethernet, for example, you've heard of that. That actually is a specification that in the OSI model encompasses both the physical and data link layers. An Ethernet connection defines not only the wired connection and the voltages that are present, but also defines how addressing is done between nodes, and how the maximum number of bytes that can fit in an Ethernet packet, and things like that. So the physical layer converts between representations of digital data inside the computer to that that's used actually on the wire. Um, uh, it defines, the transmission rate and synchronization, the physical topology where it's node to node, or perhaps, although you don't see these in use much longer, but token ring topology, whether all the nodes are arranged in a ring, or a star topology is quite common. nowadays with the individual PCs and devices all connected directly to a router or a switch. Above that, physical connection is the data link layer. So doesn't deal with connections or electrical voltages, but rather the framing, how a packet is actually formatted. There's typically a header. What's the format of that header in the data packet, and then that after the header is typically the data. Defines the physical addressing that's used, any flow control, do packets have to be acknowledged? Error control can be present in that level. I think Ethernet uses a basic checksum. Access control, who can access the network. Above that, the network layer provides for passing data beyond the local network. It also provides for, I mentioned like at the data link layer may have a specific limit on a packet length. Let's say it's 1,000 bytes. Then how do you pass a gigabyte file from one computer to another? One has to be broken up into much smaller packets that can fit in on the data link layer. But then how do you keep track of those packets and put them together in the proper order at the destination? So it can respond to service requests from higher layers and issue requests down to lower layers. So it's concerned with logical addressing and also routing. How does the data I want to send across the network get to its ultimate destination? And there often are multiple routes that can be taken between two network nodes. The transport layer provides transparent data transfer between end users. For network programmers, this is really nice. You can make a connection, a TCP connection across the internet to a remote computer and send data back and forth. And things like packet sequencing and error correction and all of that is taken care of automatically by the transport layer functions. So it's concerned with what's called service point addressing. So you can actually have multiple channels of communication between two computers. I mean, you may have what's called multiple TCP connections. You can be having a connection to a server that's serving up a web page, while also a secure shell connection, while maybe a file transfer connection, or multiple web server connections to the same computer. Okay. Session layer provides a mechanism for managing a dialogue. So when does a connection start? When does it stop? It also supports full duplex or half duplex operation. The presentation layer deals with how the data should be formatted. In particular, if you're passing floating point numbers, what particular floating point presentation is used, whether the data is encrypted or compressed. That's all handled at the presentation layer. And then the application layer defines the highest level protocols that define how files can be transferred back and forth between nodes, or email or directory services exchanged. Okay. Now, again, that was one of the first network models, this OSI model. The internet actually uses a different model. It's a 5-layer model instead of the 7-layer OSI model. The lower 4 layers correspond to corresponding 4 layers in the OSI model. And then the application layer of the TCP/IP model encompasses the 3 topmost layers of the OSI model. So the mapping is like this. Actually, as part of the TCP/IP model, the data link and physical layers in the OSI model are not specified. So TCP/IP can actually take place, networking can take place across Ethernet or token ring or fiber. Those are all specifications down here at this lower level, and TCP/IP doesn't actually specify that. So the IP part of TCP/IP is concerned with the OSI networking model. Here's where each computer is assigned a particular IP address. I'll talk more about that in just a few minutes. But then how packets use those IP addresses to actually get from one computer to another anywhere in the world. In the transport layer, primarily, I should go back to the network layer. So there are other protocols defined here at the IP layer. In addition to IP, there's what's called ICMP, Internet Control Message Protocol. That's used by the ping command. You can use the ping command to see if you have a network connection to a remote computer. There's also Internet Group Management Protocol that you can actually join a multicast group, so you can have a single server sourcing information to multiple clients. DHCP is a service by which your router may assign IP addresses to all of the various PCs, printers, whatever, which are on the local network. So it's commonly used these days to dynamically assign IP addresses to all the different nodes that are on the network. And I'll talk more about that in just a little bit. And then the open shortest path first is actually a routing protocol. So back up at the transport layer, again, 2 common ones that are used in the TCP/IP networking are TCP and UDP. So again, for the programmer, the network programmer, they would specify the type of connection they want, TCP or UDP. TCP ensures that the data makes it across error-free. UDP does not. So UDP is typically used for streaming audio and video, where if there's an error in a byte, you're not really concerned with it. The highest layer, the application layer in TCP/IP maps, actually encompasses all of the functions in the top 3 layers in the OSI model. And so here you may not have heard of these various acronyms. You probably certainly heard of HTTP or HTTPS. That's the application protocol that's used for serving web pages across the internet. So you're using that protocol whenever you connect to a web server. Some older ones that are not much in use anymore are like FTP. It's an older protocol for transferring files. It's a file transfer protocol, but it's not very secure. So it's not used much anymore. Instead, files are typically transferred using, if you're going to transfer them securely, using SCP, Secure Copy Protocol. Telnet, again, was an older protocol that allowed you to log into a remote computer, but the password, the login password was sent just in text across the network. So that allowed someone to actually capture your password if they could break into the network. So again, that's not used much these days. Instead, another protocol, SSH, is used instead for a secure remote login. SMTP is a simple mail transfer protocol. It's still in use for transferring mail between internet servers. DNS is the domain name service. That's the service that actually translates the name of a server into an IP address. So, actually when your computer, when you're using your web browser and connecting to Google or something like that, what your local computer first does is uses domain name services, contacts a server to say, hey, I want to make a connection to google.com. Then the domain name server actually passes back to your computer the IP address of that remote computer, and then that IP address is actually stored in the network packet, and the network packet is routed to the remote server. Okay, so again, a little more on the IP. Provides connectionless best effort service. This means that there's no guarantee that the packet by IP that the packets are actually going to get through. There's no error checking or even tracking done to make sure that the packets get there in the right order. That all has to be taken care of and is taken care of at a higher layer. That's the purpose of TCP. The packets can even take different routes to reach the same destination. It does take care of breaking large data streams down into smaller packets so that they can fit on the different lower level data links. Okay. This ICMP, I mentioned, that is a companion protocol to IP. You can query server to see if you've got a connection to it. And a common way to do that is to use the ping command from a client to test to see if you've got a connection to a remote computer. The Internet Group Management Protocol, and I mentioned that was used to maintain and join a multicast group. And then the Dynamic Host Control Protocol is used to dynamically obtain an IP address on your network. I'll talk a little bit more about that in just a minute. Again, in the early days of the internet, it was common for local network administrators to assign static, fixed IP addresses to all of their computers, all of the computers in the network. That was fine, for small networks. They could maintain a table of IP addresses. You have to make sure that all of the computers on your local network have a unique IP address so that you can tell them apart. As the networks grew, maintaining that table was time consuming, was something best handled by a computer actually. That's the purpose of dynamic host configuration protocol. Nowadays, if you use DHCP, when you turn your computer on, it automatically contacts the DHCP server and is assigned an IP address to use then. Internet routing protocols are used by routers to maintain paths, how to get from one network to another, and there's several different algorithms for doing that. Okay. The TCP, this actually isn't about TCP, although it's titled TCP. This deals with the application layer. Again, encompasses the top 3 layers in the OSI model. And this slide talks a little bit about a particular algorithm for generating a routing table between routers. Okay. We're transitioning from one version of the Internet Protocol, IP protocol, to version 6. I think version 5 was a research version that's never actually going to be used. But here's IP version 4. We'll talk a little bit about IP version 6. So this is the IP version 4 header. So actually there's a version here, number, and that would be 4 for IP version 4. And then the next 4 bits is the header length in bytes. There's another one here that's the total length of the packet that's up to 16 bits. Let's see some other information down here that's very important. There's the source address. This is the IP address, and it's 32 bits long, of the computer that's sending out this packet. Okay, and then it's sending it to the destination address. So this would be the 32-bit destination address of the remote computer. Okay, so let me flip over to a whiteboard and talk a little bit more about this. Okay, so generally these days, you know, every PC on a local network has, you know, an IP address that it identifies it somewhere on the internet. Okay, and it also has an underlying what's called a hardware address that's used for link-to-link communication on the local network. Okay, you may have several devices actually connected to a router. Okay. And if 2 PCs on the same network want to communicate back and forth, you know, the data will typically be passed to the hub or switch, and then directly to the other PC, say if these 2 want to communicate. Okay, so these have IP numbers. The router also will have an IP number. Okay. In addition, there are what's called the MAC address, which is another identifier. But the MAC address is just used on the local network. So the Ethernet packet, Ethernet routing is actually done using the MAC address. So the Ethernet packet here from this PC, the destination address would be the destination address of the router. In that packet would be the ultimate IP address. And again, if it's on this local network, the router would pass it to a PC here. If it's not on the local network, the router would send it on to, you know, another router. So the internet is really just a huge connection of routers. This may be connected to its own local network with PCs here, or, you know, other routers. You can have multiple connections between routers, and so it's this hierarchy with all of these routers everywhere actually in the world connected together. And so when your PC actually sends a packet to a remote computer, it doesn't know the route to get there. It just says, oh, it's not on this local network, I'm going to send it to the router. And then the router may say, oh, I know how to get there. You know, it's got a small route table. If it doesn't, it'll send it to another router, and then presumably it'll work its way up the tree of routers and then back down until it finds the ultimate destination. Okay, so a couple things with regard to IP addressing. I'm using Windows here, and I can get the IP address of my Ethernet adapter. I'm using a wired Ethernet on this computer. I've got actually a couple of other Ethernet connectors that are virtual, 2 for a VPN, and then one that's used by VirtualBox. But here's my actual physical Ethernet connector. on this PC. And a couple things to notice here. One is the physical address of this adapter. This is an Ethernet adapter, and this is what's known as the MAC address, or the hardware address of this particular adapter. And then all the adapters on your network are supposed to have unique MAC addresses. Presumably, this will be unique for all Ethernet adapters in the world. But again, this address never propagates beyond the local network. So that's important. Because that's how the Ethernet packets get from one location to another on the local network, using the MAC address. Also see down here, I've got this local computer has an IP version 4 address, so that's the address on my local network of this computer. So all other computers on this local network should have different network addresses. Notice mine is 192.168.1.3, and associated with that IP address is also the subnet mask, which notice here is in decimals 255.255.255.0. The IP version 4 address is a 32-bit address. It's remembering a 32-bit number in decimal can be it's not easy to do, so it's actually broken down into 4 bytes, and then we typically talk about the corresponding decimal value of each byte. So each of these 4 numbers can actually vary between 0 and 255. So you'll see the network address, the IP address of this particular computer is 192.168.1.3. The subnet mask is used so that I can differentiate between other computers on this network and then computers which are not on this network, and then therefore have to go out to my local router to get elsewhere in the world. The router that's used here for my home computer is this is the IP address for my router, 192.168.1.1, and so any traffic that's destined for another IP address is actually sent. An IP address that's not on my network is actually sent to the router. I see that my router actually serves as my DHCP server as well as my DNS server. So the DHCP server here, when I power on the computer, it actually assigns the IP address to this computer. Okay, I could find the IP address of other computers. So here I'm pinging google.com, and actually this is returning, these are IP version 6 addresses, so they're much longer than 32 bits, but we'll talk about that next time. We're transitioning from IP version 4, which uses 32-bit addresses, to IP version 6, which uses much longer addresses. And actually with a site like Google, they actually have several servers all mapped to this same name. So if you try this ping command, you may get a different address. If I ping, for example, okay, evansville.edu, you will probably all get the same reply. I did try earlier, server.evansville.edu, and I used a comma instead of a period. And I get the IP address that's done by domain name service, and here it says I'm getting a response, the request timed out. That's actually just CS servers configured so that it's not responding to pings actually. So they've got this particular service turned off at CS Server, but you should get this same IP address number back if you ping CS Server from your local computer. Okay. So let's see, just a little bit more about IP addresses. Let me go back, and I've already forgotten. 192.168.1.3, 192.168.1.3, and the corresponding network mask is 255.255.255.0. Okay, so the network mask actually, if you notice here, 255 would be all ones for this corresponding byte, all ones, and then the lowest byte of the network mask is 0. Okay, when the network mask is ANDed with the IP address, I get 192.168.1.0. This is the network address. Okay. Okay. And that's obtained just by ANDing these two. And then what's masked off here is the lower byte. Okay, so that means I can have up to 256 hosts. They don't have to be PCs. It might be printers, PCs, cell phones, whatever, all connected to this particular network. So, for example, my router is on this same network, 168.1.1. My printer is 192.168.1.10. Okay, these devices are all on the same network. So when my computer wants to send data to my printer, it knows that it's actually, by using the network mask, it knows that it's on the same network, and so it doesn't have to go beyond the local network. But what was CS Server? It's 192.195.228.35. Okay. 192.195. I can't remember. 228.35. Okay. Now, this is on a different network. It's not on my 192.168.1.0 network. So an IP packet going out from my computer with this IP address, when it gets to the router knows that this IP address is not on my local network. So it's going to route it away from my local network to another router, onto another router. All these routers have routing tables that would ultimately get the packet back to CS Server. Now, embedded in this packet is my return address. Okay, so CS Server can then address a packet back to me across the internet. So ultimately, and this may go through several routers. Indeed, I looked this morning, I think it went through like 10 different routers to get from my PC to CS Server. But then the packet contains my IP address, 192.168.1.3, and CS Server responds the same way. It's on a local network with other computers, and it has a network address. And the network address and network mask is used for the router to identify which PCs are connected to this local network, and then which packets then need to be addressed, sent on to another router in order, or somewhere else on the internet. Okay. So that's a brief and fairly quick overview of TCP/IP Networking, um, uh, we'll continue this discussion next time. I'll talk about wireless IP networking and then also IP version 6.